Okay, so I'm sure everyone can see my
This
screen.
call is now being recorded. This call is now taking notes.
Can everyone see my screen? Okay, so today I want us to be looking at reflection of light. Reflection of light. We've done light and we've done waves, and then we talked about properties of wave, and one of those properties is reflection. And today, as a topic, we'll be looking at reflection of light. So I need to change this in. Down here a bit. All right. So, if you recall vividly, based on the last previous lessons we have under wave, we said that reflection is simply the bouncing back of a wave anytime it intersects with a surface. All right. So, under reflection of light, we can simply say it is just the bouncing back of light waves whenever light intersects a surface. Anytime light is being struck against any surface, the bouncing back of that light wave is what we call reflection of light. And anytime this occurs, two things, we have basically two types of reflection. We have the regular reflection, and we have the diffuse reflection. So we have regular reflection and diffuse reflection. Now the question is, what is regular reflection? Now, regular reflection occurs when rays of light, incident on a smooth surface. So I have a smooth surface like this. Assume this to be a smooth surface. Then I have rays of light being struck on that smooth surface. What happens is that the reflection that is being produced is called a regular reflection. And in this regular reflection, both the incident ray and the reflected rays are always parallel with themselves. So as these incident rays are coming in here, these are my incident ray. Let me put the arrow showing incidence. Now, if they're going to be reflected, they'll be reflected also parallel. So reflection occurs this way. This one occurs this way. Please, my diagram might not really show exactly what's the lines might not look parallel, but have it in mind that in regular reflection, that both the incidents, if you are drawing your own with ruler, please ensure the incident and the reflected rays are all parallel. All right. So they have to be parallel with themselves. They are always parallel. So the incident ray and the reflected rays are usually parallel in a regular reflection. And in regular reflection, have it in mind, it has to be on a smooth surface. So it occurs only on smooth surfaces. So the figure we have here is just to explain regular reflection. And then under the diffuse reflection, The only difference is that in diffuse reflection, the reflection occurs on rough surface. So let me say I have a rough surface like this. Like this, my line here indicates rough surface. And then I have parallel rays of light being incident on the rough surface. So take note that these rays of light coming in are all parallel. So if you draw yours, also ensure the lines are parallel. So these are parallel rays of light. And then when they want to reflect, they are going to reflect in various directions. So this one can reflect this way. This one reflects this way. This one reflects this way. This one reflects this way. This reflects this way. So I have the reflection of these rays occurring in various directions. So you can see that the reflected rays are not parallel like that of the regular reflection. So even though the incident rays were parallel when they struck the rough surface, but when they began to reflect, we have the rays being reflected on various directions, making the reflected rays not parallel. So this is what we mean by diffuse reflection. So in diffuse reflection, have it in mind that the rays of light, parallel rays of light, incident a rough surface, and the light rays scatters of various directions. So this is what we mean by diffuse reflection. All right. A good example of a regular reflection is your plane mirror. So your plane mirror will give you a good example. So you stand before your mirror, you see exactly what you are in front of the mirror. That's because the way the rays are being incident is exactly how they are being reflected. But on a diffuse surface, you can see that the light scatters of various directions. A good example of that can be the reflection of light on the pages of your paper, the pages of your book, right? So the reflection on a hardwood and the rest of that on bricks. So you can see that you can't really see the exact image the way it is. The way the object appears is not exactly what the image shows. That's exactly because the light rays are being reflected on various directions, making us to see an image different or somewhat different from what the object is given. All right, so take note of that. And then we have the laws of reflection. That's the next thing I want us to look at. Laws of reflection. Having understood the types, we have to look at laws of reflection. What are the laws of reflection? The first one says, I'll just be speaking, maybe you can write or just listen. The laws of reflection says that the incident ray, the reflected ray, and the normal ray at the point of incidence all lies on the same plane. I repeat that. The incident ray, the reflected ray, and the normal ray at the point of incidence all lies on the same plane. Now, that's the first law. The second law says that the angle of incidence is equal to the angle of reflection. I repeat that. The angle of incidence is equal to the angle of reflection. Now, what are these two laws saying? Now, let's assume I have a surface, a flat surface here. I'll just use a single ray of light to illustrate what I want to say now. Now, I have the incident ray coming in this way. Of course, the ray is also going to be reflected in this direction. So let me put the reflection on this direction. Now, this is a normal line. This hash line I'm drawing here is a normal line. What exactly is a normal line? A normal line is simply an imaginary line that intersect or that bisect that surface at 90 degrees. The reflecting surface, the line that intersects perpendicular with the reflecting surface is called the normal line. So perpendicular meaning that the angle between the normal and the reflecting surface must be 90 degrees. So this is my incident ray and this is my reflected ray. And according to the law says that this incident ray, let me label it incident ray, and then this one, which is the reflected ray, at the point of incidence, which is this point here, all lies on the same plane. You can see that. So this line I drew here is called my normal. And take note, the normal is not a ray, the normal is just a line. And that is why I chose to use a dotted line to depict my normal. And also the second law, which says that the angle of incidence is equal to the angle of reflection. So meaning that the angle here, which is the angle the incident ray makes with the normal, let me call it I degrees. All right. And then another angle here, which is the angle the reflected ray makes with the normal, let's call it R degrees. These two rays, these two angle is going to be what? Equal. And that's what the law is saying. All right. So take note of that. So having understood the law, the next thing I want us to look at, having gotten this, is the reflection of light or images formed on plane mirrors. Images formed on plane mirrors. So let's look at a plane mirror. Everyone of course here should have known what a plane mirror is. So how are images formed on plane mirror? Images formed on plane mirrors. All right. Now the truth is that when an object is placed in front of a mirror, now rays of light from that object is being incident on the mirror. Now, the rays are then reflected, and it appears as though they were coming from behind that mirror. Do you understand what I'm saying? Now, you stand before a mirror. Many of you must have stood, in fact, everyone in this class, both of you must have stood before a mirror. And then you know that when you stand before a mirror, it looks like you are being formed inside the mirror. Now, the reason why that is possible is because that is what I'm trying to explain here, that it looks like the reflection appears to be coming from behind the mirror, meaning that the image of that object is formed at the point where the reflected ray meet or appears to meet, which is why the image formed looks as though it's behind the mirror. All right. So we have few characteristics of images that are formed on a plane mirror. So anytime you keep a plane mirror, there are few characteristics or few things you need to know for images formed on a plane mirror. The first thing is that the image formed on a plane mirror usually have the same size as the object. So if I keep an object before a plane mirror, the image formed is going to have exactly the same size as the object. All right. So that's the first characteristics. So I'm going to write the image. Remember, we are talking about the characteristics now. The image has same size as the object. Same size as the object. Now, that's the first characteristics. Now, what is the second characteristics? The image formed is also a virtual image. Now, students always ask this question: what exactly is a virtual image? So when we say the image formed is a virtual image, the image formed is a virtual image. Now the question is, what then is a virtual image? Now, a virtual image is simply an image that cannot be caught on a screen. What does that mean? I repeat, a virtual image is simply an image that cannot be caught on a screen. Meaning that if you stand to see yourself on a mirror, your image doesn't form on that mirror. It's not actually on the screen. It is formed inside. It is formed inside, which is the reason why if you stand at a distance away from the mirror, the image formed will also have the same distance as you were standing before as you are standing before that mirror. All right. So if you are standing 2 meters away from a mirror, the image will be formed exactly 2 meters away from that mirror. That's what we are saying. So if that happens, we say that such an image is not virtual because it looks as though the image is formed behind the mirror and not on the screen or on that mirror. Do you understand that? So the image formed is usually virtual. That is another characteristic or property of what images form on plane mirror. The third property you must know is that the image has lateral inversion. So you can say images are laterally inverted. Images are laterally inverted. Laterally inverted. So this is the third property for images that are formed on a plane mirror. Lateral inversion simply means that if you stand before a mirror, your right hand becomes your left hand and your left becomes your right. Your right ear becomes your left and just like that. So there'll be like, since the image is opposite the object, all right, the image formed is going to stand directly opposite to the object. So it will cause what we call lateral inversion. So if you are standing before, your right becomes your left and just like that. And that is what we mean by laterally inverted. Now, the fourth property also is that the image distance behind the mirror is equal to the object distance in front of the mirror. The image distance, I've explained that the image distance behind the mirror is equal to the object distance in front of the mirror. In front of the mirror. So this is the fourth properties or fourth characteristics of images formed on a plane mirror. So take note, I'll repeat. The first one is that the image is virtual. Another one is that the image has the same size of the object, meaning that the image does not magnify. If you are fat, you don't become slim. If you are slim, you don't become fat. So there's no diminishing, there's no magnification. We have exactly the same size as what we put before the mirror. The image also have a distance in front of the behind the mirror as the object distance in front of the mirror. Also, the image is not a real image. We call such an image a virtual image. Now, what happens when I incline two mirrors? So if I incline mirror, let me write that as a heading, inclined mirrors. Inclined mirrors. Now, if I bring two parallel mirror, two plane mirror, and then I incline them such that an angle is being formed. Example, let's say I have a mirror like this. This is a mirror. This is another mirror here. I put them in such a way that it creates an angle, theta. Now, let this be the side that does not reflect in the mirror. Let this also be the side that does not reflect on the mirror. So it means that the reflecting surfaces is what created this angle here, angle theta degrees. Now the question is, what is the number of images that will be formed when plane mirrors are being inclined? So if mirrors are being inclined, what becomes the number of images that will be formed? Now, this number of images formed depends on the angle of inclination. All right. So what does that mean? Anytime you have or you are being asked question regarding to inclined mirrors and they ask you to find the number of images formed, this can be obtained using the formula that number of image n is equal to 360 divided by the angle theta minus 1. So this is how we know the number of images that is being formed on a plane mirror. We use the formula n, where n means the number of images, is equal to 360 divided by theta, where theta is the angle of inclination, then you subtract 1 from it. For example, now I said, I can give you this question, that if two mirrors are inclined at angle 90 degrees to each other, what is the number of, how many images will be formed? All right. So it means that in this question, the way I said it now, that two mirrors, please, are inclined at an angle 90 degrees with each other. How many images is going to be formed? So this is what I mean by 90 degrees. I have a mirror, I have another one here, such that their inclination here is 90 degrees. So this is also the side that does not reflect, and this is the side also that does not reflect. So the reflecting surfaces made an angle 90 degrees. And then they want us to find how many images is going to be formed. So I'm going to use that formula that the number of images formed n is going to be what? 360 divided by theta, which is 90 minus 1. And this becomes, if I cancel out the 0, 36 over 9 will give me 4, and 4 minus 1 will give me 3. So it means that 3 images is going to be formed if I incline the mirrors at 90 degrees with each other. All right. Also, what if I now change the angle of inclination to what? To 60. So instead of the images to incline at 90 degrees, I incline them at 60. So the inclination, I can have something like this. 60 degrees should be maybe something like this. If here is 90, so we can just assume 50 degrees. Even though the diagram, you don't need to draw it. I'm just trying to show you. You can try these things out on your own. So if this is 90 degrees, so here is going to be 60 degrees, all right? So we have the two mirrors being inclined at angle 60 degrees with each other. And now we want to find how many images is going to be formed. Still the same formula. It means that n becomes 360 divided by the angle 60 minus 1. And if I divide 36, 360, 60, 0 cancel 0, 36 divided by 6 is going to give me 6. And 6 minus 1 will simply be what? 5. So it means that a total of 5 images is going to be formed if the inclination is exactly 60 degrees. And this is how to solve the questions and the rest of that. So once you are given the number of the angle formed and your asked number of images, don't forget this formula that n is equal to 360 over theta minus 1. All right, so moving on. Let's look at reflection on curved mirrors. We've looked at that of plane mirrors. Let's now see reflection on curved mirrors. So let me write that as a heading. Reflection on curved mirrors. This topic is a very broad topic. I just hope we can be able to cover at least the theoretical aspects. Maybe we might not do calculation as much as, let's just see how far we can go. So reflection on curved mirrors. Have it in mind, we have two types of curved mirrors. We have two types of curved mirrors. We have the concave mirror, and we also have the convex mirror. So we have the concave mirror and we have the convex mirror. Now, what is a concave mirror? Imagine having a glass sphere. Imagine having a sphere like this. Let's say this sphere is made of glass. And then I cut through this sphere like this, such that it's actually a hollow sphere. I'll be having something like this, and then having something like this. If I silver coat this side, what I'm going to such that this inward here becomes the reflecting surface. Remember I said the sphere is made of a glass. So if I silver coat, meaning that I put a silver coating behind, and then it means that the inward is going to be the reflecting surface. What I have is called a concave mirror. But if I silver coat the inside like this, such that the reflecting surface is now the side protruding outward, what I have is called a convex mirror. Don't forget that. Now the question is, what then is a concave mirror? So a concave mirror or a convex mirror? A concave mirror is simply a kind of mirror, is a curved mirror in which the reflecting surface is curved inward. Meanwhile, for the convex mirror, the reflecting surface is curved outward. So I've just explained that. And then the nature of images formed depends on formed on these mirrors, especially let's begin with the concave, will be strictly based on the position of the image. But before I talk about that, there are a few things I want us to talk about based on this diagram. So remember, I've talked about a concave mirror. I say for a concave mirror, it is simply a curved mirror in which the reflecting surface is what? Curved inward. So it means that the outward is the silver coated area, the inside is where the reflection occurs. All right. So if I'm to take off this diagram here, just hold on a little bit. So this is my concave mirror here. Now, there are a few things you have to note anytime you are dealing with concave mirror. There are a few things you must note, and those few things are being captured in this diagram I have here. In this diagram. Let me try to extend this one. Let me zoom out a little. Let me try to extend this line a little bit outward. All right. So what I have here is simply a concave mirror. In this concave mirror, the black region is the silver coated region, and the side that is ash in color is the reflecting surface. Now, there are a few things I want to define anytime you are dealing with a concave mirror. Now, this concave mirror, this point here is called the pole of the mirror. Usually it's been labeled P, even though it's not labeled in this diagram. It's called the pole of the mirror. The pole is simply the center of the reflecting surface of a concave mirror. Don't forget that. The center of the reflecting surface of a concave mirror is called the pole. I repeat that. The center of the reflecting surface of a concave mirror is called the pole. And that's exactly why that the point I labeled, I just made thick on red ink. All right. Now, the next thing you have to know is the principal axis. The principal axis is this line I drew here, all the way from here. It cuts through the center of curvature. It cuts in between the pole, and then it runs this way outward. All right. That line is called the principal axis. So if you're being asked to explain the principal axis, simply put that the principal axis is an imaginary horizontal line that passes in between the center of curvature, passes in between the focal points, and then runs through like that. That is what we call the principal axis. So it's an imaginary horizontal line that cuts through the center of curvature and the pole of a concave mirror. And that's exactly what we have here. And I told you that the pole is simply the center of the reflecting surface of the concave mirror. Now, the next thing you have to know, and that's this line I drew here, means is the principal axis. Principal axis. All right. Now, the next thing we have to learn, or I want you to know, is the focal point. Focal point. Another name for the focal point is called the principal focus. All right. Focal point. Now, what is the focal point? The focal point is simply that point where every ray on this mirror is going to converge. So every convergence that is being made on a concave mirror must be on the focal point. It must be on the focal point. So the point of convergence, another name, I forgot to say that. Another name for a concave mirror is a converging mirror. A converging mirror. So don't forget that. So you can see that in your OBJ, which of these is can a concave mirror also be called? Stuff like that. So don't forget that a concave mirror can otherwise be called a converging mirror. It therefore means that a convex mirror can otherwise be called a divergent mirror. So why is a concave mirror called a convergent mirror? Because every ray can be converged at the focal point. That's exactly what it is. So the point where these rays converges on the concave mirror is called the principal, is called the focal point. The focal point or the principal focus. Yes, either one goes. So the principal focus or the focal point is that point where every ray on the mirror converges. Now, the distance from this focal point to the pole is called the focal length. I repeat that. You can see the label in there. The distance from the focal point to the pole is called the focal length. Now, the question is, what then is the center of curvature? Now, the center of curvature, remember that this concave mirror here was cut out from a sphere. Let's imagine this sphere. Let's complete this diagram. Now, look at this diagram I drew here. This is my concave mirror here. This diagram here is my concave mirror. And now, if I complete this sphere the way this diagram is showing here, the center of the sphere from where the concave mirror was being cut out from is called the center of curvature. That's what we are saying. So just have it in mind, the center of curvature is just like the center of the sphere, where from the center of the sphere where you cut out that portion of the concave mirror. Don't forget that. So the center of curvature is the center of the sphere from where you cut out, from where the concave mirror was being cut out from. And that's exactly what this diagram here talks about. All right. Don't forget the horizontal line, which is imaginary because it's not something seen. It's actually called the principal axis. The center of the reflecting surface is called the pole. And then I said this center of the sphere in which the concave mirror was being cut out from is what we call the center of curvature. And that is what this diagram here is pointing at. So this point here is called the center of curvature, and it is assumed to be the center of the sphere from where we cut out this portion of the concave mirror from. Don't forget that. And the distance from the center of curvature to the pole is called radius of curvature. These things are very important because in exam, you can see things like write short notes on the following terms. Write short notes on the following terms associated with concave mirrors, and then they will list them out for you. So don't forget that the distance from the convex, from the reflecting surface to the center of curvature, that distance is called radius of curvature. So it can be either from the pole to the center of curvature or from any point on the reflecting surface to the center of curvature. We call that distance the radius of curvature. Don't forget that. And I think that is that for this diagram. So I've been able to explain a few things: the principal axis, the pole, the focal length, the principal focus or the focal point, the center of curvature, and the radius of curvature. These things are very, very important. Now, the point is that images that are being formed on this concave mirror depends on where the position of the image lies. So if I keep an image here and I keep another image here, the place they will be formed will look very, very different. They are not going to be exact at all. So images formed on a concave mirror depends on the position of the object on that or before the mirror. For example, now let's go to this diagram here. I have 6 different diagrams, and I'm going to use this 6 diagram here to explain various positions of images formed on a concave mirror. Now, the first one I have is if the object is kept in front of the focal point, if the object is kept in front of that focal point. Now, this is my focal point. Don't forget, I'm talking about this image here now. Look at the focal point, and point B, which is what I have here, that is where the object, that arrow you drew that is being drawn there, is actually an object. We use the arrow to depict our object in this diagram. So you can literally see when the object is inverted or when the object is standing erect. All right. So that short arrow that is being drawn from B to A is actually the object. That's the object being kept in front of the focal point. Now, if an object is kept in front, is kept in front of is being kept in front of the focal point, the image that will be formed will be formed behind. The image will be formed behind the mirror. Images formed behind the mirror, remember, is going to be a virtual image. So don't forget that. So if I keep an object in front of the focal length of a concave mirror, now I'm going to have an image formed behind the mirror. That's the first characteristic. So take it down. So if an object is being kept in front of a concave mirror, so what I'm trying to explain is just various images that is formed based on their locations in a concave mirror. So you can put that as a heading if you care. And the first I'm talking about is that if the image is kept in front of the focal length, in front of the focal point of that concave mirror, where and how will the image be formed? All right. And I said, if the object is kept in front of the focal point, the image formed is going to be what? Virtual. That's the first characteristic. So the image is going to be what? Virtual, meaning that it's not real. The image will be magnified, meaning that the image is going to be bigger than the object. So you can see that this arrow formed here is bigger than the arrow formed here. You see that? So the image is going to be what? Bigger than the object. That's the second characteristic. Now, the third characteristic is that the image will be formed behind the mirror. Clearly, you can see that, which is exactly why the image is virtual. So image will be formed behind the mirror. Behind the mirror. That's the third characteristic. All right. So we are going to have a virtual image. We are going to have a magnified image. We are going to have an image formed behind the mirror. And then the fourth characteristic, which is the last, is that the image is going to be what? Upright. So let me write it here. Image is going to be upright. So you may be asked to write out characteristics of images formed when the object is kept in front of the focal length of a concave mirror. The first characteristic is that the image formed must be upright. The second one, the image formed must be virtual. The third one, the image formed must be magnified or it will look bigger. The last one, the image must be formed behind the mirror. So these are the characteristics of images when the object is kept in front of the focal point of a concave mirror. Now let's go to the second diagram. The second diagram, if the object is kept exactly at the focal point, that's what the second diagram is talking about. If the object is kept exactly at the focal point. So look at this. I have an object kept exactly. You can see at point F, I have an object kept exactly at point F. That's it here. The object is kept exactly at point F. Now, anytime an object is kept at the principal focus, and then you want to find how many images or what is the nature of the image that will be produced when the object is kept on the principal focus. Now, the truth is that the image will be formed at infinity. So you are not going to see any image at all. The image will be formed at infinity. So you keep on looking for the image, you won't see the image, even though the image is kept in front of the mirror. All right. So if you keep the object even though the object is kept in front of the mirror, if the object is kept in front of the mirror exactly at the focal point, the image formed will be what? Formed at infinity. So your eyes can't see where the image is being formed. And that is why you see, look at these rays of light. I want you to take note of this diagram because many a times you might be asked to sketch or to illustrate with the aid of a diagram the nature of an image formed in a concave mirror. If the image is at a certain distance, they'll give it to you. So if the object is that, if the object, I mean, not image now, if the object is kept at the focal point, the image is going to be formed at infinity. All right. So look at the ray of light. The ray of light went this way, it incident this way, it strikes here, it reflects through the principal focus, and then went this way. All right. Now, this other ray hits at this point, it also reflects back at the same direction. So I have both the incidence and the reflection occurring at the same direction. In this one, this is the incidence and this is the what? Reflection. So you see, there will never be a point of convergence for this line because these two lines are parallel. They are just very, very, very parallel to each other. And of course, you know that parallel lines can only meet at infinity. So they can't meet at all. So you can't tell us that this is where the line will converge. And since there is no converging point for this line, we say that the image that will be formed when an object is kept on the principal focus or the focal length or the focal point, of a concave mirror, that image is going to be formed at infinity. Don't forget that. Now, look at this third diagram. In the third diagram, let's assume the object being kept between the principal focus, which is otherwise called the focal point, and then the center of curvature. So this is my center of curvature, and this is the focal point. And then I have an object kept between the what? Center of curvature and the what? Focal point. So what would be the nature of the image that will be formed? That's exactly what we want to look at now. Now, look at the light rays. The light rays goes from here, it hits here, and then reflect to the focal point on this direction. The light ray from here also goes through the focal point, hit here, and then reflect back on this direction. Notice that this is my reflection. This is my incident, please. That first arrow there is my incident, and this one is my reflection. This is also my incident. This is also my reflection. That is what the arrows being drawn there is talking about. So if this be the case, let me clear off everything. If this be the case, it means that the image that will be formed, we can see the point of convergence here. This point of convergence, I have an image formed here. The only difference is that the image is now looking what? Inverted, and is looking bigger than the object. So look at the object here. The object is here, kept in between the center of curvature and the focal point. Look at the object, but the moment the image of the object is being formed, the image now looks inverted, and then it's looking somewhat bigger than the original object. So hence, we can say that if an object is kept between the center of curvature and the focal point, that the image formed is going to be, number one, the image is going to be what? Inverted. Inverted. The image is going to be inverted. Number two, the image that will be formed is going to be a real image. Is a real image because it is not behind the screen. It is not behind the mirror. It is in front of it. So it is on that mirror. So we call such image real image. Unlike in this case, where we have a virtual image. Now, the third thing you have to know is that the image is going to be what? I've talked about inverted. It's going to be magnified. Magnified in the sense that it will look somewhat bigger than the original object. So the image will be inverted, the image will be real, the image will be magnified. And do I have a fourth property here? I've talked about magnification. It will be real, it will be inverted, and then it will be formed after or behind the center of curvature. That's the third one. The image will be formed behind C, where C there is what? The center of curvature. Don't forget, the image must be formed behind the center of curvature. That's the third one. That's the fourth one, It has to be formed behind the center of curvature. So let me write it behind C. That's what we have there. So these are the properties of images that will be formed when an object is kept between the center of curvature and the focal point. All right. So if I move to the next diagrams I have there, now look at this one. What if the object is kept exactly at the center of curvature? That is what this fourth diagram is talking about. What if the image, the object is kept exactly at point C, which is the what? Center of curvature. Now look at this. The light ray went this way, it hits here, it reflects this way. You can see that. Another light ray went this way, it hits here, it reflects this way. Always know that this light, you can see that the convergence here is at that focal point. All right. That's why I said that the focal point is where convergence takes place. Now, notice this is what we have in this diagram. Let me clear the lines off so we can have the original picture. All right. So see, the image that is being formed is looking inverted, but it has the same size as the original object. Don't forget that the image that is being formed is looking inverted, but it has the original size of the what object, even though it's looking inverted, but it has the same size. So this object here, the size of the object here is equal to the size of the image here. The only thing is that the image is now looking inverted. So meaning that if I keep an object exactly at the center of curvature, these are the few characteristics you will notice. Number one is that the image is going to be what? Inverted. Number two is that the image is going to be real. It's going to be real. Why? Because it's not formed behind the mirror. It's formed in front, all right? It's not behind. Now, the third one is that the image is going to be the same size with the object. And of course, the fourth one is that the image will be formed exactly at the same point C. That's it. So the image will be formed at point C. So it is kept at point C. The image will also be formed at point C. And that is the characteristic I want you to know. So the image will be inverted, the image will be real, the image will have the same size, and the image will be at what? Formed at the same point C. And this happens only when the object is kept on the center of curvature. All right. That's the fourth one. Now, the fifth one, if the object is being kept behind the center of curvature. If the object is being kept, look at the object here. If I keep the object apart, afar, or behind the center of curvature, what becomes the nature of the image that will be formed? All right, so this is the object. That's what I try to sketch here. This is the object here. All right, so look at this object. The rays of light goes from here, incident here, it reflects. Let me draw that again. It goes through this way. Remember, the reflection must always be through point F. So it reflects through this point F here, this way. All right. I have another ray of light going this way, going this way. Then when it hits here, it also reflects at this point. Now, this one goes this way and then reflect at this point. That's the meaning of those rays they put there. So the diagram is looking terrible now. Let me pull out those my lines, all right? But just try to master how the lines are being sketched, because many a times you might be asked to sketch this diagram. Now notice, this is the point here. The object is at this point. Look at the image formed at this point. You see, the image is formed and is in between C and F. So when the object is kept behind C, we have an image formed that is in between C and F. So the image will be formed between the center of curvature and the what? Principal focus, which is otherwise called the focal point. But the only thing is that the image is going to be looking what? Diminished. The image will be looking smaller. So I have a bigger image, but I have a bigger object, but I have a smaller image being formed. And the formation will be such that the image formed will be between the center of curvature and the principal focus, otherwise the focal point. So let me write a few characteristics of images when they are kept behind the center of curvature. The first one is that we have a real image. So the image formed is going to be real. Second one is that the image formed is going to be diminished. The image formed is going to be diminished. The third one is that the image formed is going to be between C and F. Between C and F. And of course, the last one, what will be the last characteristics I've talked about real, is going to be that the image will be inverted. You can see that the image is looking inverted. It's looking inverted. The object is standing upright, but the image formed is looking inverted. You see that? The image is going to be real. Why? Because it is not formed behind the mirror. All right? The image is going to be diminished, and the image will be formed between C and F. And now, that is that for that. When the object is kept away from the center of curvature, is kept behind C. That's what we have there. Now, the last diagram, which is the sixth illustration, is when the object is kept at infinity. All right. So if the object is at infinity, where will the image be formed? The image will exactly be formed at the focal point. The image will be formed exactly at the focal point. That is it. Remember, when the image is kept at the focal point, look at this. When the image is kept at the when the object is kept at the focal point, the image formed, which is diagram 2, that's what I'm trying to explain. The image that will be formed at infinity. That's what we are saying. And now, if I keep the object at infinity now, the image that will be formed exactly at the focal point. And that's what this sixth diagram here is talking about. So these are the few characteristics or the few things, the few characteristics and properties of images formed in a concave mirror based on their location. Their various location tells us what will be the nature and the size of the image that will be formed. Now, if you observe everything we've talked about, you will notice that in every case, it is only in one case that we have a virtual image. So a virtual image is only formed when the object is in front of a focal length. If the object is kept in front of the focal point, please, in front of the focal point. If the object is kept in front of the focal point, that is the only time a virtual image will be formed. And that virtual image is what we have in diagram 1, the first diagram, where we have a virtual image that is looking upright and magnified. All right. So that is the only time a virtual image is being formed for a concave mirror. Every other time the image is going to be formed will be what? Real. The image will be formed real. At every other position, we have real images at every point, except when the object is at focal point, the image will be formed at infinity. Of course, infinity, we don't even know where and how. No one can approach that. All right. So that's what we're saying. But in a convex mirror, every time we talk about a convex mirror, every image produced in a convex mirror is always what? Virtual. The images produced in a convex mirror is usually what? Virtual. So it doesn't matter the position of the object. It doesn't matter where you kept the object. Provided it is a convex mirror, it will always give us virtual image, virtual image, virtual image. Don't forget that. And virtual image, the image will be looking magnified, which is to say it will be looking bigger than the object. All right. And then it will be formed behind the mirror. It will be formed behind the mirror. And don't forget what a convex mirror looks like. We've talked about concave so far. The convex is just like this. So I have here to be the silver coated area, meaning that, let me take back the diagram. Wait, the diagram here. So I have here to be the silver coated region. So this curve, the side that is being protruded outward is actually the side that reflects. All right. So when rays of light incidents on this surface comes like this, it will just scatter. The rays of light will just scatter, right? It will diverge. That's what I mean by that. So rays of light comes like this, it will diverge. So this will diverge this way. This is the incident ray coming, then this will diverge this way. which is why the convex mirror is called a divergent mirror. So if the rays diverge, it means that there is no time a real image will be formed, because these two rays can never meet. They are moving, this one is moving to the north, this one is moving towards the south. So they can never meet a point of intersection. So meaning that their intersection point will be to trace them behind the mirror. So if I trace these two rays behind the mirror, I'll get a point where the image is going to be formed. And that point is actually behind the mirror. So images in a convex lens or in a convex mirror or a converging mirror usually forms behind the mirror. All right. And it's usually what? A virtual image. That's the point. But for the concave mirror, they are all real, except when the object is kept in front of the focal length. Then when that in front of the focal point, when that happens, then we have a virtual image that is looking magnified being formed on the mirror. So take note of that. And that's a few things I want us to know. Okay. And don't forget also, I've not given us any equation, even though we might not be able to use to solve these questions or to solve question with the equation, but let me give it to you, which is the mirror equation. I'm sure every one of you should have come across the mirror equation. So if you are solving a question that involves mirror, you have to know the mirror equation. The mirror equation. The mirror equation is simply an equation that shows us the relationship between the object distance, the image distance, and the focal length of that very mirror. And what is the formula? The formula says that the inverse, okay, let me write it out, 1 over u, where u is my object distance, plus 1 over v, where v is my image distance, should be equal to 1 over f, where f is the focal length, where f is my focal length. And don't forget what focal length is. The focal length is simply the distance from the pole to the what? Principal focus or the focal point. That length there is what we have there. So the inverse of the object distance, which is 1 over u, and the inverse of the image distance, which is 1 over v, is going to be equal to the inverse of the what? Focal length. So this is called the mirror equation. And with this, we can calculate problems involving mirrors. All right. And then don't forget that the focal length f is equal to the center, the radius of curvature divided by 2. So sometimes you might not be given the focal length, but if they give you the radius of curvature, if you divide it by 2, then you are going to get the focal length. And that is that for this class. I actually have an engagement exactly by 9:30. I would have want us to take more time and solve few problems, but I'm sorry we may not be able to do that. And I'm sure we've learned few things from this class. So please, what I want you to do for me, the formula is simple. You can try out questions by yourself. In case you encounter difficulty, you can just do well to write me on WhatsApp. I will clarify you on anything that confuses you on this. But I've taken my time to explain the position of these images. Firstly, we talked about plane images, plane mirrors. We talked about the properties or the characteristics of plane mirror. We talked about images when they are inclined, how we can solve the number of images formed when mirrors are inclined, how we can find the number of images. And then we talked about the curved mirrors, and then which are the concave and the convex. And I've taken my time to explain how that the images will be formed and where they will be formed at various positions of a concave mirror. And I said for a convex mirror, it is always a diverging mirror. Hence, we have all the time a virtual image will be formed, which means that the image will be formed behind the mirror. And this is where I want us to end the class for today. So ask me your question, just in case you have any. Does anyone have a question? Okay. If there's no question, as I said, if you encounter difficulty, you can do well to just reach out to me and I'll give you clarifications, especially concerning the formulas that I've written down. So at this point, I may just end the class now. Wish you guys success in your exams. Golden and Obaumi, the other person left. So wish you guys success, and I want you to read harder, prepare harder, and anticipate to smash your exams. Have a good night, everyone. Thank you for the reactions. I really do appreciate it. And as I said, this may likely be our last class. About me, this may likely be our last class. All right. Take care. Bye.